Quickly, my name is Amy Dunn-Ruiz. Welcome, and I'm so happy to have you guys join me today. We're going to look at the 2019 free response problems from the AP exam for Calc AB. If there's any BC folks out there, I have those problems handy as well. If you want to pipe in a little later, I'm happy to talk about a question or two there. Aaliyah's BC, excellent. Hi, Perla, good to see you. Okay, so let's see. Can you see the slide with the fiveable on the screen there, folks? Can you give me a emoji if you can see the first slide there? Alrighty. 1 second, wrong thing. Alrighty, okay, so problem number 1 is an in and out problem. Has fish in a lake. Oh, it went away. Oh no, it went away. Hold on. I will get it back, I promise. And is it back? Can you see slide number 1? Yes, you can see it? Yay, okay. Thank you so much. I appreciate your guys' feedback. Love the alien face, Akshita, that's great. Okay, I can't tell what Brechnia's emoji is, but you see the timer. Don't worry about the timer. Okay, so problem number 1 says we've got fish entering a lake. That's an in and out problem. Alrighty. Problem number 2 is a velocity of a particle problem. We're justifying, this is just the first 2 parts of the problem. We've got a Riemann sum. We've got having to look at velocity, finding the distance traveled. You can't read the problems. Gosh darn it. Let's see. Hang on. Problem number 2 continued. Anyway, it's a particle. You've got a table with information about the velocity there. Problem number 3 is you've got a graph and you have to analyze the function based on lots of information given to you. You've got a fundamental theorem of calculus issue in there. You got some limits in there. Problem number 4 looks like a related rates problem. You've got a, what are they calling it this time? This is a cylindrical barrel collecting rainwater. Problem number 5 is a region enclosed, and we are going to be probably rotating that guy. I bet we're finding the area, we're finding cross-section shapes, and we're rotating around a axis. And yes, in fact, this particular problem is part of the material that's not included for AB this year. It is a BC only topic just this year, but it was on last year's test. So probably we won't focus on this one. And then problem number 6, we've got some just real function interactions. We've got this L'Hopital's rule being mentioned and all that. So let me go back here and see if you guys are interested in, let's see, I've got my poll. Oh, look, you guys have been voting already. It looks like number 1 and number 6 are the big winners. I'm gonna give you another, let's say 30 seconds for you to enter your vote on the poll. Problems 1, 2, 3, 4, 5, 6. Again, 5 is probably not worth us going over at the moment because it is an AB only topic. If there's BC people that want to take a look at that, we can do that towards the end of the video. Okay, well, definitely number 1's a winner. So why don't we start there, and then I'll come back and see what else we need to look at. So I'm going to switch the screen. Let's hope I can do this. I'm going to switch the screen to my clipboard here so we can talk through the problem together. So I'm going to close that one out, and hello, I'm going to share my clipboard, and Alrighty. So once again, I got this. Yay! Thank you so much for the vote of confidence. Problem number 1. Oh, graphing calculator required. Let me zoom this in a little bit more. This is one of our favorites. It looks like the in and out type problem. Everybody's got a graphing calculator handy. If you don't, you probably can do the graphing part on Desmos or some other graphing functionality. I think we might have an integral we're going to want to do on the graphing calculator as well. So let's get going. So problem number 1 says, I'm going to move this dumb thing up out of the way. Oh, technology, so great. Okay. All right. So we have fish entering a lake modeled by the function e. And E is given by this formula here. E of t is 20 plus 15 times the sine of pi t over 6. And we have a fish leaving the lake. So here we have them entering the lake. That makes sense. E is for enter. And we have fish leaving the lake at a rate modeled by the function L, L for leaving. Alrighty, and that's 4 plus 2 to the 0.1 t squared power. And E of t and L of t are measured in fish per hour. So those are rates of change. And t is being measured in hours starting at midnight. So time equals 1 would be 1 a.m. All right. Can you give me an emoji? Can you hear me okay? And can you see the problem okay? Hooray. Thank you so much, folks. And I'm actually going to move this. Things won't go away for some reason. Okay, so I'll try and hide it behind my picture. Alrighty, so let's look at part A of this particular problem, which says how many fish enter the lake over the 5-hour period from midnight to 5 a.m. Give your answer to the nearest whole number because a decimal portion of a fish is just gross, I guess. So one thing that's really helpful to remember anytime you're going into a calculus situation that involves rates is if you integrate a rate of change, you're going to get the change in amount of that thing. So we're going to look at this rate of fish entering, because we don't care about them leaving on part A, just entering. And the rate is in fish per hour. So if I integrate, it's sushi. Yeah, hilarious, guys. If I integrate the rate of fish per hour, that's going to give me the change in the number of fish over a certain number of hours. Alrighty. So it's from time 0 to time 5. So take a moment, think about what would you do to solve this problem. I'm not sure if it's easy enough for you guys to type in on the chat or not. Go ahead and do that. Also, while you're thinking about what you're going to type in there, do know that there's an ask a question button that you should be able to, I believe for you, it's at the bottom of your screen. Feel free to throw a question in there. People can upvote it or downvote it if we get enough questions. But that's where you can put a specific question for me, and just so it doesn't get lost in the shuffle of the chat over here. So Shant hates tuna but loves salmon. Okay, that's a sushi related comment, I think. So we're seeing antiderivative, integral, same. Don't be a third derivative, haha. Okay, yeah, so we are going to integrate. We are, for part A, we are going to integrate, all those answers were wonderful. We're going to integrate from 0 to 5 because that's our time range that we're looking at. And we're going to integrate E of t because that's the rate of fish entering. So we're going to integrate 20 plus 15 sine of pi t over 6. Oops, close that first parentheses. And of course, that is with respect to time. Now, this is actually a problem that you absolutely can integrate by hand. There's nothing impossible about integrating this guy by hand, but it's a calculator-friendly problem on the AP test. And it just in order for you to get used to making sure you have enough time on the AP test, let's use our calculator. And also so we can get through more problems here. So I'm going to integrate Math 9, if you have a TI, from 0 to 5. And you go ahead and use your calculator while I'm doing this. Make make sure that you are in radians and that you're plugging everything in properly. And I'm going to do 15 times the sine of, and that's pi times t. And of course, my calculator, I'm just going to use an x because we're smarter than our calculators. And in this mode, x is the only variable I can use. So we're just going to go with that. That's all over 6. Close that parentheses. And that's with respect to x. Alrighty. And so we pop that in. And I got 153.457. But of course, 45769 even, 01. The directions were to round this, excellent. The directions were to round this to the nearest whole number. So this, got to remember back to, 7th grade math. Yes, you should absolutely be in radians 100% of the time when you're using a calculator in calculus. I know physics, you use degrees a fair bit, but make sure Tuesday morning, make sure Sunday morning of next week, you have verified that your calculator is in radians, absolutely, positively. So I'm rounding to the nearest whole number, which is here. I look to the next digit, which of course is a 4. And so that's going to round down to 153 fish. And actually, you got it, fabulous. 153 fish enter the lake, because we want to put our word problem answer in words. I'm going to just kind of drop some words here to get it quickly. But 150 fish enter the lake in the 5-hour period, or from midnight to 5 a.m., something like that. Yes, we round down. Because you just look at the very next digit, the 576901 doesn't matter at all. Because this guy is between 0 and 4, we round down. If it was between 5 and 9, we would round this guy up to a 4. Alrighty? Yes, we would round down. Wonderful. If you were asked to round off to the nearest 10th, which would be 1 digit after the decimal, we would look at then the next digit, and that would tell us to round this guy up to 153.5. But that wasn't the actual question. We were asked to round to the nearest whole number. So you only look right here, nothing else right here, and that tells me just leave it as is. Alrighty, let's look at part B. Okay, I don't see any other. So 153 fish is the right, it's not could it be the right answer, it is the right answer. You do want to verify though, you want to add entering the lake from midnight to 5 a.m. Nara, just to be kind of repeating part of the question and the answer to be super clear that you get, you understand the context of the problem. Alrighty, Perla, I see your comment. I don't know about the rule that you're talking about. It very well could be true, but the kind of the accepted rounding that you're expected to do on the test is just like this. And in general, if they don't tell you to round, you want to go to 3 digits at least and farther in the middle of a problem. If you have to round off in the middle of a problem, take as many digits as your calculator will give you. Awesome. Okay. Part B says, what's the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m.? So we're thinking about average value of a function, of course, and that average function that we're looking for is fish leaving the lake. Okay. So think about what sort of process will we go through to find average value of fish leaving the lake? Average value of fish leaving the lake. And of course, I see some people referring to 153, Andrew, that you're on to something there, but this was entering the lake, and we're actually now talking about leaving the lake. So you're thinking about, Andrew, you were thinking about the average value of fish entering the lake. Yep, okay. Okay, oh, good. Q exist. You got it, good job. Good job, good job, good job. Yes, so I'm seeing lots of good answers in Yarrow, Connor, Daniela, Nara, wonderful. Yes, so for part B, I think I'm just gonna slide this around. For part B, what we wanna do is average, right, average number leaving. And anytime you're asked for an average value of a function, what you wanna do is, well, there's two ways to get it, but if you have the function they're looking for, we want the average number of fish leaving, right? So what we want to get is the number of fish leaving over the time that, the time that went by. So we are looking at 5 minus 0 being the time on the bottom. And what we want on top is the number of fish. And hang on one second. We want the average number of fish that leave the lake. So we're going to want to integrate and get our value from 0 to 5 of the number of fish leaving. So that is going to be the integral of the L function. And of course, that L function is 4 plus 2 to the 0.1 t squared dt. So we're integrating our rate of fish leaving and dividing by 5. And Daniela, once again, you're one step ahead of me. So that's going to give us the number of fish over time. And that is going to give us, I'm going to integrate 0 to 5. And I see a bunch of you are already doing that already. Excellent. And we want 4 plus 2 to the, 2 to the, what was it, 0.1. And then I'm going to use x squared power, and that is with respect to x. And then, of course, I have to divide this whole thing. Once I get it, I want to divide that by 5. And that was an average number. So we are going to leave the decimal values there. So that gives us about 6.059 fish per, you're going to write fishies. Okay. Fish per hour. Right? That's the average number of fish leaving the lake. It's like the average rate of change of the fish. Okay, 6.09 fish per hour. Alrighty. And then part C, we'll release that here. In part C, we are trying to, pardon me. In part C, we want the greatest number of fish in the lake. What type of a problem are they asking you for here? Do you remember the name of this type of problem? Optimization, maxes and mins. Specifically, what kind of max or min? And since it's greatest number, I think we'll just stick with max. Yep, Q, you got it. Anybody else? This is an absolute max problem. We're looking for the greatest number of fish in the lake from the entire time, from time 0 to 8. So we are using the endpoints. Akshita asked, are rate in and rate out problems exempted? I am not aware of that. However, I think average value problems might be exempted from it. Some of the applications of integrals are exempted, but to be completely honest, I kind of feel like it's not no harm, no foul to go over these, because all of these topics really do sort of end up kind of braiding together in the big picture of everything. So if we understand these skills, it'll help us kind of understand the other skills as well. So will velocity and acceleration problems be in the exam? As far as I know, yes. Again, it's the rotating of a region around an axis. The three-dimensional volume problems are not on the test, and some of the application of integral problems are not on the test. Area between curves, I believe, is exempted, yes. But again, if you learned it, it really is kind of part of that bigger picture of integration, and it certainly doesn't hurt to do a problem or two related to it. We won't spend time on that one problem today, but it's certainly, you don't want to like just flush that information out of your brain. It really all is interrelated. Okay, part C, wonderful. Part C, again, we're looking for this absolute max for this particular time frame from 0 to 8. And we're looking for the greatest number of fish in the lake. Don't forget, this is a calculator-friendly problem. So can't hurt probably to take a look at the graph of what's happening with these rates. Remember, E, way up here, E of t was the rate in, and L of t was our rate out. So one thing we could do is graph E of t minus L of t. That would be the change in fish overall, kind of the global change in fish per hour. So I'm going to go ahead and type that in. I'm going to type 20 plus 15 times the sine of pi x over 6. Close that parentheses, close it again, and then I'm going to subtract from that the L function, which was 4 plus 2 to the 0.1 x squared power t squared technically. And let's take a look at the graph of that guy. Now my scale is a little wonky here, so I'm going to let it graph, and then I'm going to go back in and fix the window. And since we're looking at 0 to 8, oh, look, I have 0 to 7. That's silly. Let's change that from 0 to 8. And my y, this is left over from another problem. So let's go, I don't know, how about negative 20 to positive 20 and see what that looks like. Got to fix the top there. I know it's going to cross back through right around there. Okay. So we'll go just up a little higher. Let's call it 35. Okay. We are in radians, Aaliyah, absolutely, tootly. Always, no matter what, without doubt, in calculus, we will be in radians. Something might once in a while be mentioned in degrees, no problem, it's okay to double check. But anytime you're doing calculator work, anytime you're solving some sort of related rates problem and you get an answer that relates to angles, it's always going to be radians. All right, so here's our graph. I'm just gonna kind of sketch the graph here as well, because if I was taking the AP test, I would want to kind of show my evidence here. And of course, this is time, and of course, this side is E of t minus L of t, or the overall rate of change of fish in the lake, and that is going to be in fish per, was it hours? Yes, fish per hour. Alrighty. So what do I know? And we haven't figured out what this point here is yet, but what do I know about all of this stuff where the graph is above the x-axis? What do I know is happening here versus what is happening over here? Can you figure out what is going on the graph there? Nara's got it. Good. Yes, yes, yes. So since this graph is the rate of fish entering versus leaving, so the overall rate of change of fish, when we're in this region where the graph is above the x-axis, we have a net positive increase, as Nara put it. We have more fish coming in. And then here where that rate is below the x-axis, the rate is negative. We have more fish leaving, right? So if you think about it, and I don't think we were given an initial value. Were we? No. Right, we were not given an initial value, so we don't know how many fish we started with. But for instance, perhaps there's a given number of fish in the lake at time 0. From here to here, we've got the number of fish increasing. And then when we hit this time, all of a sudden the number of fish are decreasing. So let's find that critical point. Akshita is one step ahead of me. Let's find that critical point using the calc. So we're going to go second and then calc. We don't use trace to find the exact value. And I want to find the 0 of that function. I'll go a little to the left. Again, that was second calc that I hit. So this is asking me for a left bound. So I go a little bit to the left of that 0. Boop. A little bit to the right of that 0, boop, and then a guess, there we go. and it gives me that x value, or actually that's a t value in our context, is 6.2035644. I wrote the whole darn thing down. So did Akshita. Good job. Good job. So that's this critical point here. That's where we change from fish increasing to fish decreasing. Now we wanted the greatest number, and remember we do have to think about, when you're talking about a absolute max, you do need to think about endpoints, which would be t equals 0 and t equals 8. And we need to think about critical points, which is t equals about 6.20. I'll round it off to here. That 5 there tells me I'm going to round that guy up to a 4. So approximately 6.204. Okay. So that is the critical point. Sorry, I'm reading your questions here. The number of fish is increasing. Do we find when the function reaches 0 to get your answer? Yes. So we figured out where the rate was 0, and we figured out where the rate went from increasing fish to, or fish, the net amount of fish going up to the net amount of fish going down. Now I don't know how many I started with, and I don't know how many I finished with, but I could integrate and get this area under the curve here could tell me exactly how many fish overall, the net increase of fish from time 0 to time 6.204. And I could integrate from here to here and figure out the net amount of fish that we lost overall from here to here, from time 6.204 to time 8. But technically, the question was, when was the fish the greatest number? Daniela got an absolute maximum of 135.015 fish. That would be assuming, I believe, that you start off with 0 fish in the lake, and they didn't actually give us that amount. So you could start off and say, hey, a of 0, or let a of 0 equal, some unknown value. You could call it x, right? And then, okay, a at 6.204 is x plus, and I'm going to integrate from 0 to 6.204, my e of t minus L of t, right? The actual functions. So I could do that. I could find that increase in the amount of fish. I'm going to go through this process, but I'm actually going to show you that it's not actually necessary in the great long run of things. So integrating from 0 to 6 point, and actually I'm going to use the whole number, 6.2035644, because just why not be obnoxiously long here? And we're integrating 20 plus 15 sine of pi x over 6, close it, minus, open, 4 plus 2 to the 0.1 x squared, close it, that might be too many parentheses, dx. And I got 100, and I think somebody else said this before. So this is x plus 135.0149, let's call it. So at time 6.204, I have a little bit more than 135 more fish than I did at time 0. Do I know exactly how many fish? No, because I wasn't given exactly how many fish at time 0. And now I can do a of 8, which would be this plus this, plus, I guess, I'm going to integrate from 6.204 to 8, e of t minus L of t dt. But what do I know for certain at time 8 because of all this? What do I know for certain? It's less. Yes, we're going to be losing more fish here. It would definitely be less fish. And the question was, when is it the greatest number, right? So for certain, we know we had the greatest number of fish at that critical point. So there's a couple things you could do. You could go through and show this, and you could find this and show that this value is going to subtract, and you will definitely have less fish. So you can go through those steps just like you would any absolute max problem. You also could kind of write out in words your reasoning that because before this critical point, the number of fish was increasing, and then after that critical point, the number of fish was decreasing. Thus, by logic, the highest absolute amount of fish had to be at 6.204 hours approximately. Alrighty, so that was part C. Let's take a look at part D. Part D says, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? And actually, the rate of fish increasing or decreasing. By the way I drew the graph, this isn't going to answer the question specifically for us, but this was 0.6203. This is approximately time equals 5. So just by kind of looking at the graph that I had, I can already sort of approximate or estimate that the overall rate of change sure seems like it is decreasing or going down, okay? I think to be really specific, it probably would be wise to just verify that. I mean, you could say it visually looks like it's decreasing, but a really simple thing to do also is just verify and prove to the grader, hey, I'm worth a 5. Give me a 5 on this test because I know that rate of change is what's the magic word? What is a rate of change in calculus language? Daniela got it? Yes, so derivative is what we're talking about. Slope, derivative, instantaneous rate of change. So let's take a derivative with respect to time of that E of t function minus the L of t function. Now, we can go through the process of taking that derivative. I'm about 30 minutes into this problem, and I kind of feel like I should go on to another problem. So I want to remind you, on a calculator-friendly problem, you can use the derivative function, n-deriv, boom, and I'm going to derive with respect to x in this case at what, I need to type in the function. So 20 plus 15 sine of pi x over 6. And then actually I'm going to put one more. I'm going to insert another set of parentheses just right there. I don't need it, but I kind of like to be like, there's my first function, and now minus, I'm going to subtract the whole second function, which was 4 plus 2 to the 0.1 t squared power, or x squared in this case. And that we're going to find that at exactly t equals, and that was at time 5, I believe. Yes, at exactly time 5, boom. And we do verify that it is a negative. So that gives me negative 10.72, and I'm going to round it off to 3.722. And I look at the next digit is a 7. That tells me to round that up to 0.723. So since our slope there is negative, again, the question was, is the number of fish increasing or decreasing? Since this value is negative, we would write out that the number of the fish is in fact decreasing at that time. Good question, Daniela. Okay, so a couple things I want to roll back through my comments here and address a couple of questions. One, Perla said a couple minutes ago, my teacher always says that charts and graphs are counted as personal reference and not as an explanation. However, I think that anytime you're using your calculator, it's very wise to show what you see on the calculator and how you're getting that information from it. I've never heard that it's only counted as personal reference. I think it's a great way to back up your justification, but you always do want to explain clearly. And here, again, I didn't write it out, but you would definitely give an explanation as to why that is, in fact, the time at which you have your absolute max. And then another question, why are we taking a derivative? Yes, it is already a rate. But again, this says, is the rate of change increasing or decreasing, right? So what's the slope of the actual rate, right? So we're trying to, Oh, and Venkata is explaining that for you. Thank you. You're trying to see if the rate of change, which is this E of t minus L of t, is at its moment increasing or decreasing. At the moment on that graph, clearly it was a positive value, right? That rate was positive, but was actually decreasing. The value, we were getting closer and closer to 0 on that overall rate. Is it necessary to show what you see on a calculator? I think the rate of change, first derivative, increasing or decreasing. Right. Is it important to show what you see on a calculator? I always tell my students to do a sketch of what they see on the calculator. Usually in the rubrics, you're not going to see the graph. I just think any sort of backup evidence that you have to show, and if you're relying on the calculator to do some work for you, I think it's worthwhile to show what evidence you were looking at. If you say the rate of the rate is negative as a justification, is that okay? Yes, but again, you want to put things in terms of the context of the problem. And so what I would say is the rate of change of E of t minus L of t is negative, meaning that the rate of change of the rate of change of fish is negative. If you say the rate of the rate is negative, yes. Okay. Next up is on the poll, you guys voted number 4 to be the next most positive. Oops. Alrighty. I'm gonna grab something while we're at it. Okay. So let's take a look at problem number 2. Problem number 4, I mean. I'm looking at the rubric real quick on problem number 1 and just verifying that yeah, because the derivative of those rates is less than 0, the rate of change of the number of fish is decreasing. That's all they needed to show, was showing this line that the hide my poll here, showing this line that you're taking the derivative, or you could say E prime of t minus L prime of t. It's another way of saying the same thing, equals this, which is less than 0. All right, let's go forward to problem number 4, which was the next most popular, and this is our related rates problem. The cylindrical barrel. Alrighty. We've got a cylindrical barrel with a diameter of 2 feet, and that is a constant diameter right there of 2 feet. And it is collecting rainwater, so we've got rainwater flowing into it. Pardon me for just a second. Alrighty, we've got rainwater flowing into it. And through a valve not shown at the bottom of the barrel. So we've got a certain amount of water being collected, and then it's draining out of the bottom. The rate of change of the height h of the barrel, this rate of change here, this is changing, with respect to time is modeled by this rate right here. So dh dt is -1/10 square root of h. H is measured in feet, T is measured in second, and of course, as usual, they gave us the volume formula for a cylinder. That's pretty typical that they'll give you the formula, which is pretty handy. Alrighty. So part A asks us, as I slide this up just a little bit, find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet. So we want the rate of change of the volume of the water. What should we start with? Here's a formula for volume. What is our first step on a problem like this? Again, it's related rates. And do you remember the type? Nara says derivative. Do you remember the type of differentiation you need to do here? There's a special name for it. Absolutely. Implicit differentiation is the type of, you forgot it existed. It's okay. Implicit differentiation is what we're going to use. And in general, with implicit differentiation, especially on a related rates problem, you want to start with sort of the basic relationship problem, right? You want to start there and then use your implicit differentiation. One thing I think is really helpful and important is plug in any constants first. Don't plug in any variables, but plug in any constants first. And we happen to know that the diameter of the whole thing is a constant, therefore that radius would be a constant. If you forget to plug that in, it's not a deal breaker. You still can get the problem right, and I'll show you why in a second, but really helpful to just plug that in. So we were given that the diameter was 2 feet, which means our radius is 1 foot. So if I plug that in, pi times 1h, well, that's a much simpler problem to take the derivative of implicitly. So we're going to get dv dt, and pi, of course, is a constant, and h, the derivative is dh dt. Now, before we finish this problem, I just want to remind you, if we had used and left r in as a variable, we'd get dv dt equals, and then you'd have to use product rule. So first of all, I'm having extra steps, which means I might make extra mistakes. So I get pi r squared dh dt, and then plus pi 2r dr dt times h, blah, blah, blah. I got to plug things in. The thing that will kind of, hopefully a little light will go off on your head when you get to this point and you realize, what is dr dt? Oh yeah, the derivative, or excuse me, the diameter isn't changing. Therefore, the radius isn't changing. So the dr dt is 0, which means this whole portion is 0, which means this is really all I needed in the first place. And since r is 1, I would have ended up right here anyway. So in general, plug your constants in first, but definitely not your variables. So now we're here, and we're trying to find rate of change of volume, which is dv dt. So I have pi times dh dt, which was given to us. Boom. And I can, let's see, I know that h at this moment, they told me when the height of the water is 4, so I'm going to plug in 4 for h. So, sorry, I know you can't see that anymore. We're going to get negative pi times square root of 4 over 10, which of course is negative 2 pi over 10, or, right, negative 2 pi over 10, and that, see, and that is going to be in feet cubed per second. Is it okay if you just leave it as dv dt equals pi blah blah blah? On the open response problems, it is okay to leave the values. I think that this particular problem is no calculator. And actually, I could reduce this to negative pi over 5 feet cubed per second. Technically, officially, you are allowed to leave your, and I think, Nara, this is what you're asking about right here. You are allowed to leave values unsimplified. Yeah, you'd have to, they specified that h was 4, so you do need to plug that in, but technically this should get you full credit. This is more simplified and kind of like what we like to see in class, and not too hard to get there on this particular problem, but yes, you are allowed to leave them unsimplified like that. Okay, part B says, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? This seems kind of familiar. So we're trying to figure out whether the rate is increasing or decreasing. You see the relationship to that last problem we just did where we were looking at was the rate of the amount of fish increasing or decreasing. Alrighty, so I'm looking for, okay, I know that the height of the water is 3 feet. By the way, on the real AP test, if they, they give you a, excuse me, not on the real AP test, in prior years on the actual AP test, you'd have a booklet and you could circle things. If you have a printer handy, which would be lovely, you can do that. But if you don't have a printer, which most of us will be in that situation during the test a week from Tuesday, I would really write down these, these key things. We're talking about height, when the height is 3 feet. Okay, so for part B, when H is 3 feet, right? And I want the rate of change of the height of water. Is dH dt increasing or decreasing, right? That's what I'm looking for here, and explain my reasoning. So just like on problem number 1, part D, was the rate increasing or decreasing? In order to tell whether that's happening, we need to look at the derivative. Once again, the slope of this thing. Okay, so what that means is I want to take the derivative with respect to time of dH dt, or I'm looking at the second derivative of the height. Alrighty, and I believe this is a no calculator problem, so I'm looking for the derivative with respect to time of -1/10 root h. And of course, I think much easier to think of that guy like that. That's h to the 1/2 power, and the -1/10, just a constant, right? So you're going to go through your process here. Okay, and I'm taking the derivative of h, but it's with respect to time. Remember, we're doing implicit again. So you're going to get -1/10. Go ahead and work out. So I wrote the constant down. Remember, a constant just sits there. What's the rest of that derivative? Can you write out what the, I know typing it out is tough, but can you go ahead and write out what you think the rest of that derivative is going to be? You guys still there? Good, Jorge. Good. Jorge, there's one little part missing. Akshita, excellent. Okay. So what we're looking at is constant stays there. Of course, we've got h to the 1/2 power, which means 1/2 h to the -1/2 power. And because we're doing implicit differentiation with respect to time, we've got that dH dt tagged on the end there. And of course, I'm just trying to figure out whether this is increasing or decreasing, this particular value. So I want to figure out basically when, and by the way, this is interchangeable with, if I wanted to use that notation, second derivative notation for h. But again, that's the same thing as the derivative of the dH dt. And I want to evaluate that when, what was it, when h is 3. So here I have -1/20, and then I have h to the -1/2 power, which means I have 1 over, and I want 3 to the 1/2 power, or square root of 3. So that -1/2 power means it goes in the denominator, and I just change from 1/2 power to square root. And then the dH dt, of course, is the original, and we can just plug that back in, right? That's, and the dH dt was -1/10 root h, right? So again, I have a -1/10 and then root h, or square root of 3. And hopefully you see that root 3 over root 3 reduces to 1. And I have negative times negative, so I have positive, and then 1 over 200. And all I really wanted to know was that value positive or negative? I verified that it is positive, so I know that since that second derivative is positive, dH dt is increasing. We have a positive slope. We have increasing at t equals, excuse me, when h equals 3, when the height is 3 at that moment. Alrighty. So again, we've kind of looked at that same idea from two different perspectives. Okay, part C, last part on this problem, is at time t equals 0, the height of the water is 5 feet. So we have an initial value right now. The height is 5 feet at time 0. Use separation of variables to find an expression for h in terms of t. Oh boy, separation of variables. That means we're looking for a specific solution for a differential equation. So again, at time 0, when t equals 0, h equals not 0, it equals 5. I lost my eraser, which equals 5. Great. Alrighty, Harper, I agree. They are all going to do great. We've gotten some great feedback, great answers so far. So use separation of variables to find an expression. I'm not sure how you're going to answer this on chat, but any ideas on how to get started on this? What is separation of variables? Well, that's a good thing, good question to ask. Akshita's getting us started by saying bring all the h's on one side and the t's on the other. That's really what we mean by separation of variables. But we need to kind of figure out where are we going to start. And really the only thing we were really given in this problem is dh dt equals this. All right. Plug into, very good. Okay, so first step is separate the variables. And so since I have dh on top over here, I'm going to divide and have the root h end up over here. And I'm going to leave this constant here because we're going to end up trying to get an h equals equation. So I'm going to leave this constant of -1/10 here, and I'm going to multiply each side by the dt. So that was the separate step. Okay. And then the second step is integrate. Okay, so we separate, so now we're going to integrate. And I'm going to rewrite this as h to the -12, just because I think that makes it a little more user-friendly. Very good. And Akshita, you had it right on the nose there. We separate the h's and the t's. We're going to integrate, and then we're going to find the c value. So let's go through our integration first. This is going to be reverse power rule, which means I want to increase my power by 1. So from -12, we're going to go to +1/2. And then we have to divide by our new power. So we're dividing by half, which is the same thing as multiplying by 2. And the integral of dt, there's no t here. So basically what's the integral of dt is just t. And I'm going to add a plus c. And that constant, because this is a indefinite integral on both sides, this constant is going to cover basically the constant from both sides. So there we have it there. So to get kind of a generic equation, I can divide everything by 2. And I'm going to leave it as plus c. I kind of tend to do that. Leave that as a plus c right there. I'm going to freeze it right here. Right? So basically I have square root of h equals -1/20 t plus c, same. And I know that when time is 0, h is 5. Right? And well, 5 is always 5, but h is 5. And we're trying to figure out kind of an equation for h, which means we got to figure out what this plus c value is. So if you plug in 0 here and 5 here, clearly c is √5. So then our overall equation, if I go back to this, I had root h equals -1/20 t plus the c value, which is √5. To get h by itself, I'm just going to square everything. So I'm squaring this whole side, I'm squaring this whole side. So I get h equals, or h of t even, equals -1/20 t plus √5 quantity squared. And the question was find an expression for h in terms of t. And voila, we have done that. Alrighty. Nobody's posed any questions on the question board. Take a look at the poll. We might have time to get into a little bit of problem number 6. That one had a couple of votes. How are we doing so far? Any questions I haven't hit for you guys? Any lingering concerns? Give me an emoji. How are you feeling right now? You still in there? You still hanging in there? Oh, Nara, you're so sweet. I'm first of all, welcome. This is only my second Fiveable stream, so my anxiety has decreased a little bit too. But I hope that you are feeling a little bit better about the AP test in a week and a half. Oh my gosh, it's a week from tomorrow. Okay, that just drove my anxiety up. The AP test a week from tomorrow, and a really good idea is to pull up 2018's free response questions or any of the free response questions that you find on the College Board. I think the number one thing you can do between now and next Tuesday is practice doing timed tests. I know that the first problem on the real test next week, they're giving you 25 minutes for, but usually for the past problems, the average is about 15 minutes. And yes, the College Board does have optional practice problems. Really good idea to grab a problem like, let's see, problem 6 was the next one that you guys had asked about, and we'll just kind of dip our toe in the water on problem number 6, which I have right here. So a typical problem like this where it has multiple parts, they're going to expect that you can do that in about 15 minutes. Is everybody going to get that 100% completed in 15 minutes? Probably not. That's why you kind of want to prioritize and look at what do you know how to do so far, and try and work as efficiently as possible, especially when it says it's calculator allowed. You really should use your calculator to help you time-wise. But again, one of the best things you can do between now and next week is kind of get that time anxiety pressure out of your system a little bit. Sit down with a couple, maybe pick 2 or 3 problems and give yourself 45 minutes from past years' problems. They're all available online, and the rubrics are all available online as well. And go through and get the idea of like, oh, I only have, oh no, the time's ticking away. You can see it ticking away. And hopefully that'll make next Tuesday be a little less stressful. That's the number one thing I've heard every year is how kids are surprised at how quickly the time goes. So give yourself that kind of practice, and I think that'll help take that edge off a little bit. Do I know how many points out of 7 will get you a 5? It's different every year. Sometimes on AB, I think, I'm not going to pull that out of the air right now, but it's Googleable, it's findable on previous years, what the scores or kind of what the overall percentages had to be. But remember, in previous years, we also had multiple choice, so that shifts it just a little bit. Let's see if we can get a little start on problem 6 here, and then we're going to call it a day. So problem 6 says we have 3 functions. Well, wait, 3 functions, f, g, and h. They're all twice differentiable. And at time 2, g of 2 is equal to h of 2, which is 4. So basically at that time 2, both of these functions just happen to equal 4. We have this line, which is going to be tangent to them. This line, y equals 4 plus 2/3 x minus 2, is tangent to both the graph of g and the graph of h at that exact same time. So first question is, find h prime of 2. Well, they didn't even give us what h was. They just gave us 1 point in time for h. So how are we going to find h prime at 2? Thinking about what do you know in the great scheme of things, what does h prime represent? Go ahead and type it in if you have an idea of what we're supposed to do here. How do I find h prime at 2? I know h of 2 is 4. And Naria, you hit the nail on the head yet again. Because this is a tangent line, and I don't even know what the graph looks like, but I know that at time 2, I'm gonna draw a sketch here. This is not necessarily at all what the graph looks like, but I know that at time 2, or x equals 2, this output value is 4 on the H graph. Again, I just drew a random sketch here. And we've got, I probably even drew it the wrong direction, but we've got this tangent line, and I'm drawing it as a negative slope. Probably not correct. We've got this tangent line y equals, x minus 2. That's a minus right there. We've got this tangent line here. And the whole point of a tangent line is that the slope of the tangent line is the same as that derivative, that instantaneous slope at that point. So, and I'm going to start fresh because this is not an accurate graph, just kind of to give you the idea. So h prime of 2 is, in fact, the tangent line slope. Right? So we can just take that y, the graph was y equals 4 plus 2/3 x minus 2. If you know anything about equations of a line, that's the slope right there, right? 2/3. But you also could take its derivative and find that the slope of y is 2/3. So I know h prime of 2 is 2/3. Okay. Part B. Get a little bit more. So this was like, do you understand the kind of the overall concepts of what a slope is? Part B says a is a function given by a of x equals 3x cubed times h of x. We're going to write an expression for a prime, and then we're going to find a prime at 2. Right, so we're going to be taking the derivative of this, and that means we're going to have to use our rules of derivatives here. So anybody see a rule off the top here that they recognize that we're going to have to use in taking the derivative of a? So a prime. Do you know the name of that rule that we need to use here? Alan, welcome. Alan, yes, you got it. Yes, yes, yes. Because I have a product of two functions of x, I need to use the product rule. The 3, honestly, is just a constant. So I can just leave the 3 and it'll be part of the product rule in each of these. Or I could kind of think of this as a 3x cubed. Either way, I'm going to leave the 3 as a constant. So I'm going to take the derivative of this guy times my h of x. Plus, there's my 3 constant. I'm going to take the derivative of h of x times the x cubed. Just like that. So a prime is 9x squared h of x and 3x cubed h prime of x. Lovely. Your job now is, what's a prime evaluated at time 2? Go ahead and evaluate that. This is a no calculator problem, so we'd want to either do the arithmetic, which is totally doable by hand, but again, as I think it was one of your peers mentioned earlier, you can leave it in a unsimplified form, but we gotta plug these guys in first, at least. Right, so I have a 9 times a 4, and h of 2, of course, was given to us way up here at the top of the problem. H of 2 is 4. And then here I have 3, and 2 cubed, of course, is 8. H prime of 2, we found that up here earlier in problem, in part A. And so I have 9 times 4 times 4, 9 times 16 happens to be 144. You can work that out on the side, or you can leave it just like this. And of course, the 3's cancel here, and I get 8 times 2, which is 16. Bottom line, it is 160, but you are allowed to leave it in this format or this format. You just can't leave it quite like this because you want to show that you know what those values are. Alrighty, part C says, L'Hopital's rule. Oh, you've all been waiting for this one, haven't you? Part C says, get a fresh piece of paper. we have a function h, and it satisfies this formula for when x is not equal to 2. And it is known that at 2, or the limit approaching 2, we can evaluate it using the L'Hopital's rule. How do we know that? Well, if you try direct substitution, you get 2 squared minus 4. That's 4 minus 4, or 0 on top. And it also tells me that since I have a 0 on top, I'm allowed to use L'Hopital's rule, that the bottom also goes to 0. Now, we haven't been told what f of x was, but what I know by L'Hopital is that I've got either a 0 over 0 or infinity over infinity. And clearly at times 2, that's giving us a 0 over 0 case. Alrighty. So it's known that we can use L'Hopital's rule. Yay. We're going to use that to help us find f of 2 and f prime of 2. That must be from your teacher, Akshita. Don't test my limits or you will have to go to the hospital. Oh my gosh. Yeah, we can have some bad jokes in math land, can't we? Alrighty, so let's start off with, do you remember how L'Hopital's rule works? The one of the conditions is you have to either have 0 over 0 or infinity over infinity, right? In fact, this is what we have in this particular problem. What do we do with that? What does that help us do here? All right, so I'm looking at my limit as as x goes to 2 of h of x, which is x squared minus 4 over 1 minus f of x quantity cubed. All right, okay, nobody has answered about how to proceed with L'Hopital's rule. Okay. Well, yes. Okay, so deal with L'Hopital's rule is if you do have a 0 over 0 or an infinity over infinity, you can evaluate that function further because you know that, not an infinity, leaving this as a 2, excuse me. We know that this limit is equal to derivative over derivative here. So derivative of the top gives me 2x, derivative of the bottom separately, I get 0 for the 1, minus, and I've got to use a little chain rule here, 3 times f of x squared, and then chain rule f prime of x. Alrighty. Beautiful. With an, yes, good job. Good job, Connor. Yes, Connor, you do know that this denominator equals 0. We're not using that quite yet, but it might come in handy that 1 minus f of x cubed equals 0. It has to be since the top goes to 0 when x is 2. So therefore the bottom goes to 0 because they told us L'Hopital's applies. Alrighty, so we want to find f of 2 and f prime of 2. Let's see. So yeah, we knew that at 2 that this whole thing goes to 0. So I guess that for solving this part right here, if I know that 1 minus f of 2 cubed equals 0, then I know that 1 equals f of 2 cubed. And I can cube root each side. Cube root of 1 is just 1. So I know that f of 2 has to equal 1. Excellent. We figured out that part. Excellent. Oh, I'm sorry. Can you see it better now? Okay. So that was the first part of the question, which was find f of 2. The next part of the question is find f prime of 2. So what do we know? We know that h of 2 is supposed to equal 4. And I also know that, I'm going to scroll up here for a second. I also know that h is twice differentiable, meaning h is differentiable, meaning even though this limit is approaching 0 over 0 when x equals 2. And again, this is what this is h of x here. Then, but this limit, since this whole thing is differentiable at x equals 2, this has to equal 4, right? So what we're saying is we can't determine it here. 0 over 0 tells us nothing, but if this limit should be approaching 4. So I took L'Hopital's rule. I did a LaHop to get from here to here, and we end up with 2x over negative 3 f of x squared times f prime of x. And so what I know, let's see if I can fit this all on the screen, is that, you like that, LaHop? I told my students, you don't have to write the whole thing. They know what you mean. Just showing that I did a LaHop. So I know that this limit, after doing L'Hopital's, times f prime of x, and this is when x is approaching 2, that this whole thing is supposed to equal 4. We know what f of 2 is now, so that's handy. So let's try some direct substitution, knowing that this thing is supposed to equal 4. So if I plug in a 2 here, I get 2 times 2 on top, which is 4. And on the bottom, I got negative 3. And then this f of 2 squared, so 1 squared, and then times f prime of 2. And this whole thing is supposed to equal 4. So I think you can see we can kind of unravel this and figure out exactly what f prime of 2 is supposed to equal. Clearly, you know, this is supposed to equal 4, so this whole denominator should be equal to 1. Couple ways to work that out, but hopefully you see 4 over 1 would equal 4, right? But basically this whole denominator has to equal 1. So negative 3 times 1 times f prime of 2 is equal to 1, telling us that f prime of 2 has to be equal to negative 1/3. Okay, that was part C. Let's get through part D, and then I will bid you all adieu. For part D, it says it is known that g of x is less than h of x for x values between 1 and 3. And k is going to be this function in between them. Does this look familiar at all? K is going to be the function in between them, between 1 and 3. Is k continuous at x equals 2? So what do we know here? Again, I'm going to scroll this up a bit, but before I do, I just want to remind us, we've got g and h and k. G and h are twice differentiable. That's what's sort of relevant on this particular part of the problem. So I know g and h are differentiable. And since something's differentiable, I know it has to be smooth and continuous, right? No corners or cusps or breaks. It's smooth and continuous if it's differentiable. So what that tells me, so since g and h are differentiable, they are continuous. And what does continuity tell me? Continuity tells me that in order to be continuous, I want the limit from both sides, for instance, at 2, I want the limits from both sides of that function to equal the actual output value of that function, right? At x equals 2, for whatever this g function looks like, not only should the limit from each side be approaching 4, but the point should be there at 4. Not a hole there and a point somewhere else, which would be discontinuous. We want actually the limit from each side to equal the output value, which is what we have here. Okay, so we know that is true and equals 4, and we also know then that this is true for h of x as well. All right, so this is sort of, the question is sort of reminiscent of the sandwich theorem, also known as the squeeze theorem, right? So what I know is that we know for sure, they told us that this is true. They told us that g of x is less than or equal to k of x is less than or equal to h of x. right? Therefore, and we're trying to figure out whether k of x is continuous. What I know then is that the limit as x approaches 2 of g of x and the limit as x approaches 2 of h of x are both approaching 4. And therefore, because this is true for this holds for x between 1 and 3, then this would hold also at 2, which means then that that limit as x approaches 2 of k of x is sandwiched between 4 less or equal to less. Therefore, this has to equal 4. Thus, there's no other way to interpret it but that the limit as x approaches 2 of k of x is equal to 4. It got sandwiched, it got smushed, squeeze theorem, so that we know that that is true. And likewise, so that was with the limits. I knew that the limit had to be sandwiched. Likewise, I know for the function, they gave me that truth for the function. Therefore, g of 2, and this is 4. Therefore, k of 2 also has to equal 4. And since that limit of k of x as x approaches 2 equals 4, therefore we have proven continuity. Pretty exciting. And really that was all kind of given to us from this initial line here, right there. So we've gone an hour 20, so I'm a little bit on the long side, but I really appreciate everybody being here and participating. I really wish you guys the best of luck on next week's AP exam. Again, my best piece of advice is definitely do some practice tests and put yourself in a timed situation, which means you might not answer everything, but at least you'll get used to that time pressure that can make you a little nervous and a little anxious. Try and get some of that out of the way before test day. Also, you are allowed to have notes handy. This is like the first time this has ever happened. So organize your notes. Maybe you have graphic organizers from your teacher, or maybe you can make a nice kind of organized, as you've gone through, organized reference page for yourself so that you can have something easy and write at your fingertips. Maybe it's a couple pages worth, but definitely easier than flipping through your textbook to have things in your own handwriting as you've gone through your practice tests. All right. Well, this has been fun, and I really appreciate you guys. I hope you've had a good time. Aaliyah, you're so welcome. Nara, lovely to have you guys here. Connor, I'm so excited for you guys for next week, and I wish you the best of luck. I miss my students. I wish we were all in the same room. You're welcome, Ellen. Adios, Nara. Wonderful, guys. Take care. All my best. The slides will be available on the afterwards when we post the stream, and I might even be able to include some of the rubric there as well, although you can absolutely Google and find the rubric on the College Board, or just find it on Google. Okay, best of luck to you guys. Bye-bye.